If you take a tangent to this r coordinate axis, then divide the tangent with the magnitude, then you will get your unit vector r cap here. Okay. Unit vector r cap like this. So at this point, if you take a tangent along the theta coordinate axis, so theta coordinate axis is like a circle, it's moving around in a curvature or a circle. So you take a tangent at this point, then the tangent at this point will be pointing along this direction. Divide the tangent vector with the magnitude, then you get what is called theta cap, unit vector along the theta coordinate axis. So at this point, your theta cap is pointing along this direction. At this point, your r cap is pointing along this direction. But the orthogonality of this plane polar system means that angle between r cap and theta cap at any point here, it is 90 degree. At any point in a space, in a 2D plane, the angle between r cap and theta cap is at 90 degree. So I hope you can picture what I mean here as a like the orthogonality of this r cap and theta cap at any point in a space. All right. So now that we finish a 2D system, let us come to the 3D system. So we are already familiar with this 3D Cartesian system. In the 3D Cartesian system, we have x-axis, y-axis, and z-axis. And the coordinate lines are x coordinate line, y coordinate line, z coordinate line. You see that coordinate lines are straight line, right? Coordinate lines, that is x, y, z coordinate lines are straight lines. Okay, coordinate lines are straight lines. Now, in addition to that, in a 3D system, we can talk about the coordinate surface. If you look at this surface, this particular surface here, something like this, the surface on the YZ plane. I hope you can picture surface on the YZ plane. If we are looking at YZ plane, for every point on the YZ plane, x value is fixed. X value is equal to certain constant. X coordinate value is certain constant. C1. All right. I need a space. So what I mean here is that if we are looking at this x, y, z coordinate system, for every point on this YZ coordinate plane, YZ plane, x value is fixed. You can have one plane here, or you can have another plane here passing through the x-axis. So over this plane, x value is 0. Over this plane, x value may be, let's say, 1, 2. So x value may be 2. All right. So as long as x value is fixed, you have a perfectly plane YZ plane. Perfectly planar YZ plane. All right. So that is what we mean by x equal to C1. X equal to C1 is the equation of the YZ plane, the equation of one of the coordinate surface. Okay, it's the equation of the one of the coordinate surface. So this coordinate surface is a plane. All right, and you can also consider another plane here, something like this. On this plane, that is the XZ plane. This is your XZ plane. On the XZ plane, Y value is fixed. Y can be 0, Y can be 1, 2, depending on where you are constructing the plane. But for every point on the plane, the Y value is fixed. So, and this surface, as you see, this surface is also planar. Okay, coordinate surface is planar. And similarly, you can consider Z equal to 3 surface here. Z equals to C3 surface. So this is also a planar surface, and here for every point on this surface, Z value is fixed. Right. And one thing you should also note here is that in this 3D Cartesian system, the angle between coordinate exists. They are 90-degree. Also, the angle between this surface and this surface, the angle between the coordinate surfaces, they are 90-degree. The angle between this y equal to C3 and z equal to C3 surface is also 90-degree. The angle between all these coordinate surfaces is 90-degree. Okay, so that is one thing you should remember. Now, there can be another coordinate system. What time is it? Yeah. There can be another coordinate system in which not all the coordinate surfaces are planar. So if at least one of the coordinate surface, so let's say instead of this 3D Cartesian system, let's say x, y, z, instead of this 3 Cartesian system x, y, z, we can consider another coordinate system defined by u1, u2, u3. Okay, similar to your x, y, z. Let's say we consider another coordinate system defined by u1, u2, u3. And in this coordinate system u1, u2, u3, if one of the coordinate surface is no longer planar system, if it is a curved surface, then such coordinate system is called curvilinear coordinate system. So similar to what we have just discussed, the coordinate surface can be defined as u1 equal to c1, u2 equal to c3, u3 equal to c3. All right, so similar to this, in the 3D Cartesian system, we have x, y, z. The coordinate surface are defined by x equal to c1, y equal to c2, z equal to c3. Similar to that, let us consider another coordinate system, u1, u2, u3 coordinate system. And the coordinate surfaces can be written like u1 equal to c1, u2 equal to c2, u3 equal to c3. And if one of the coordinate surface is a curved surface, then that curvilinear coordinate system is called that coordinate system is called curvilinear coordinate system. Okay. Now, when the coordinate surface u1 equal to c1, u2 equal to c2, u3 equal to c3, if they intersect at 90-degree, if the coordinate surface and the coordinate lines intersect at 90-degree, then such coordinate system is called orthogonal curvilinear coordinate system. Just like your 3D Cartesian system, here in the 3D Cartesian system, the coordinate line, x line, y line, z line, they intersect at 90-degree, and the coordinate surface x equal to c1, y equal to c2, they intersect at 90-degree here. The angle between them is 90-degree. Okay. And also the angle between x equal to c1 surface and z equal to c3 surface is also 90-degree. And similarly, the angle between y equal to c2 and z equal to c3 surface is also 90-degree. So in the 3D Cartesian system, not only that the coordinate lines intersect at 90-degree, the coordinate surfaces are also intersecting at 90-degree. So this 3D Cartesian system is also orthogonal system. Okay, when they intersect at 90-degree, this is called orthogonal system. And similar to that, if the coordinate lines u1, u2, u3 intersect at 90-degree, and the coordinate surface u1 equal to c1, u2 equal to c2, u3 equal to c3 intersect at 90-degree, then such coordinate system is called curvilinear orthogonal curvilinear coordinate system. Now, you can picture such a system like this. Here, as you can see, the coordinate surface is defined by u1 equal to c1, u2 equal to c2, u3 equal to c3. So, unlike this 3D Cartesian system in which this surface is perfectly plane, that is y equal to c2 surface, and this surface is x equal to c1 surface, and this surface is equal to is z equal to c3 surface, perfectly plane. Instead of having this planar coordinate surface, like in the case of 3D Cartesian. In general, the curvilinear coordinate system can have, as you can see, it's a curved surface. Curved surface u2 equal to c2, u3 equal to c3, and instead of having x, y, z coordinate lines, we have y1 coordinate curve, y2 coordinate curve, y3 coordinate curve. Okay, y1, y2, sorry, u1, u2, u3 coordinate curves. Instead of having x, y, z coordinate lines, we have u1, u2, u3 coordinate lines. And if these coordinate lines intersect at 90° at any point here, then that means this is a orthogonal curvilinear coordinate system. Now, just like when we discuss your plane polar and the 2D system, plane polar is your r theta system, 2D Cartesian is your xy coordinate system, right? Just like this, here you remember we can write x as a function of x, r, and theta, y as a function of r and theta. Also you can write the reverse as r as a function of x and y, and theta as a function of x and y. So just like that, in a three-dimensional system, we can have 3D Cartesian system and orthogonal curvilinear coordinate system u1, u2, u3. So you can write a similar transformation relation: x as a function of u1, u2, u3, y as a function of u1, u2, u3, z as a function of u1, u2, u3, and you can write the reverse transformation relation just like this. This how we write it: u1 can be written as a function of x and y and z, u2 as a function of x, y, and z. So you can do that, right? Now, so I have a hiccup. It's almost, my lecture is almost finished. I don't have time to fetch water. So like this, you can write the transformation relations. Now, how are you going to get this tangent vector? Just like we discussed before, tangent vector can be written like this. For example, in a 3D Cartesian system, position vector is what? X, I, Y, J, Z, K, right? So tangent vector along X, tangent vector along X coordinate, that you can obtain it by del R upon differentiating with X coordinates. Then if you differentiate this with respect to X coordinates, xi plus yj plus zk, if you do that, differentiation of x with respect to x is 1, so this is ik. Differentiation of y with respect to x is 0, 0. Right, so this is the tangent vector. In order to find the unit vector, unit tangent vector, in order to find unit tangent vector, what you're going to do is del r upon del x divided by magnitude of del r upon del x. So magnitude of this is 1, so this is I, right? So just like that, you can find unit tangent vector, and similarly you can also find unit tangent vector. Here in a 3D Cartesian system, as you can see, position vector r is a function of x, y, and z, right? Position vector is a function of x, y, and z. Similar to that, in a orthogonal curvilinear coordinate system, u1, u2, u3 coordinate system, position vector you can write it as a function of u1, u2, and u3. So in order to find unit tangent vector, what you're going to do is differentiate this position vector with u1, one of the coordinate variable, and divide it with the magnitude. Okay, divide with the magnitude. Then if you denote this del r upon del differentiation of position vector with respect to one of the coordinate exists variable, that is u1. del r vector upon del u1 magnitude if the magnitude is denoted as h1, which is also called scale factors. Okay, so if you denote it like this, then del r upon del u1 can be written as h1 into u1. So u1 is what? U1 is the unit tangent vector along the u1 coordinate. This is unit u1 is unit tangent vector along u1 coordinate. Okay. U1 coordinate line or curve. Similar to that, you can find unit tangent vector along u2. In order to find unit tangent vector along u2, you simply have to divide the position vector uh, r vector with respect to the coordinate line u2 and divide with the magnitude. And if you denote this as your scale factor h2, the magnitude, then you can write this as this. And similarly, unit vector along u3 coordinate line will be simply differentiation of the position vector with the coordinate variable along the u3 and divide with the magnitude. This is what you get, right? These are known as the scale factors. So as you see, you can also, in addition to the, what is that, tangent unit vectors, these are the set of unit vectors e1 cap, e1 cap, e2 cap, e3 cap. They are the set of unit vectors known as tangent unit vectors. They are unit vectors which are tangential to the coordinate curve u1, u2, u3. Unit vectors tangential to the coordinate curve u1, u2, u3. Right. In addition to these unit vectors, in a curvilinear coordinate system, we can also define another unit vectors called perpendicular unit vectors. The one we just described is tangent unit vectors. These are the unit vectors which are tangential to u1, u2, u3 coordinate curve. So I think you can understand u1 curve, u2 curve, u3 curve. Instead of x coordinate line, y coordinate line, z coordinate line, we can have a u1 coordinate curve, u2 coordinate curve, u3 coordinate curve. Okay, so similar to x, y, z coordinate lines. So instead of that, we write u1, u2, u3 coordinate lines, coordinate curve, and these are the tangent unit vectors. So we can also discuss what is called perpendicular unit vectors. So we know that what is this? This is your, let's say, your coordinate line u1. So what is this surface? This surface will be u1 equal to c1 surface, the coordinate surface, the curved surface. And this is your u2 coordinate line, coordinate curve, and this is your u2 equal to c2 coordinate surface. This is your u3 equal to c3 coordinate surface. u3 equal to c3 coordinate surface. So if you remember when we discussed gradient, I think I have proved that, yeah, we have discussed that. If we take a gradient on this, like if phi equal to c defines, if phi equal to c defines a surface, if phi equal to c defines a surface, grad phi is perpendicular to the surface. This we have proven, right? Phi equal to c surface we discussed. If we take a grad phi, then that grad phi is along the perpendicular direction to the surface that we have proved. So similar to that, u1 equal to c1 is one surface. In order to find a vector perpendicular to the surface, you simply take the grad of u1. So unit vector along this direction will be grad of u1 divided by magnitude of grad of u1, and another unit vector along the another unit vector which is perpendicular to u2 equal to c2 surface is grad of u2 upon magnitude of grad of u2 and this gives you unit vector perpendicular to this u3 equal to c3 surface, which is grad of u3. It will give you the vector perpendicular to surface u3 equal to c3. When you divide it with the magnitude, then that will give you the unit vector, perpendicular unit vectors. Okay, perpendicular unit vectors. So here you can see from this picture, here u1 unit vector, u1 cap unit vector is tangential to the u1 vector is tangential to this coordinate curve u1 at this point. However, e1, capital E1 cap, capital E1, the unit vector, perpendicular unit vector, this perpendicular unit vector is perpendicular to u1 equal to c1 surface. u1 equal to c1 surface at this point is here. This is your u1 equal to c1 surface. Okay, so this capital letter u1 cap, which defines perpendicular unit vectors or unit vector perpendicular to u1 equal to c1, is pointing along this direction. So the direction between tangent unit vectors and perpendicular unit vectors, they are not necessarily identical, right? And similarly here, this is your u2 coordinate curve. So if you draw a tangent to this u2 coordinate curve at this point, if you draw a tangent, so the tangent vector will be along this direction. Then you divide it by the magnitude, then you get a unit tangent vector. Unit tangent vector is pointing along this. But as you see, this is your u2 equal to c2 surface. u2 equal to c2 surface. When you take a grad u2, that will give you a direction perpendicular to this surface. Divide with the magnitude, then you will get the unit vector e2 cap. So e2 cap, as you can see, it is perpendicular to the surface. E2 cap is perpendicular to U2 equal to C2 surface at this point. So this perpendicular unit vector and tangent unit vectors, they are not necessarily pointing along the same direction. So we can define two sets of unit vectors in this orthogonal curvilinear coordinate system. All right. So I think I will stop this over here. And we can continue this discussion tonight at 8 p.m. There I want to discuss about gradient and divergence and curl in orthogonal coordinate system. Okay, so we will discuss all these things, and then we will get into cylindrical system, and then maybe we can complete this curvilinear system tonight. Okay, see you again tonight at 8 p.m. If you have entered your attendance, you can exit the meeting. Just type your attendance in a chat box and then exit the meeting. So I hope everyone has typed their attendance. I will exit the meeting.